So the next thing that we study under this topic kinematics is speed versus velocity. We try to see what are these two terms, what do they mean, and what's the basic difference between them. So we start with discussing speed. Speed, as a general term, as we know it, it tells us about the rate at which a body generally covers a distance, how fast a body moves or how slow it moves, right? That tells us, the speed tells us about that. The speed gives us that information, how fast or how slow a motion is covered, right? So it's the same definition that we study here in physics also. Speed is the rate at which a distance is covered by a body. So it's the rate of covering a distance. Mathematically, we define it as distance travelled per unit time, and the letter that we use to denote speed is V, small v generally. So speed V is defined as distance travelled over the time taken in travelling that distance. So this is essentially how we define speed in very basic form. As we can see, it is a distance travelled divided by a time taken. If we talk about the SI unit of speed, its SI unit comes out to be a unit of a distance, which is meters, divided by unit of time, which is seconds. So meters per second. Generally we write this as meter per second like this. Okay. Since it is a scalar quantity divided by another scalar quantity, distance by time, speed itself is a scalar. It's a scalar quantity. It only has a magnitude associated with it, right? Velocity, on the other hand, is the rate at which a body covers a displacement. So as we have already seen in the previous video, the difference between distance and displacement, the same way here we have a difference between speed and velocity. Velocity gives us the rate of covering a displacement. Rate of covering a displacement. Mathematically, V would be, now we use the same letter V to denote velocity. The only difference is that there will be a vector sign over it, because velocity is a vector quantity. It is given by displacement divided by time, or displacement covered by a body divided by the time taken in covering that displacement. So as we understand that here also displacement is measured in meters, right? The SI unit of displacement is also meters. So the unit of this quantity will also be meter per second, generally written as meter per second like this. And since velocity by definition is a vector divided by a scalar, it will be a vector quantity. So velocity is a vector. I hope you understand that the direction of velocity, as we define it mathematically, like vector V is equal to vector S divided by t, the direction of velocity vector would be the same as the direction of the displacement vector. Both the vectors will have same direction. So for a given motion, the velocity and the displacement in that time would be in the same direction. Now these two definitions that we have given for speed and velocity, they are like quite crude definitions. They are like very basic definitions. Generally, when we deal with practical situations, we deal with more refined definitions of speed and velocity, and there we talk about two distinct types of speeds and velocities. One is called the average value of speed or velocity, and the other is called the instantaneous value of speed and velocity. So let us now discuss about both of those. So from here we come to average speed versus instantaneous speed. So you might have some idea already about the average speed, at least average of any quantity. It gives us the overall value of that quantity, a kind of an average, a mean, right, over a broader, a larger interval. in this case, when we talk about average speed, it gives us the overall speed of a body over a large time interval. So, if a body has travelled for a large interval of time, then if we could just discuss, or if we could just measure the distance travelled by the body in that large interval and divide that distance travelled by time, we will get the average speed. Okay. So, average speed, if we just first start with that, average speed, which we denote by V with the subscript AV or AVG for average. So, average speed, which is denoted as this, will then by definition be the total distance travelled by a body over the total time taken in travelling that distance. Mind you, here generally we deal with large time intervals. Okay. So, when we write this mathematical definition, total distance covered, instead of writing S, or we can actually write S also, S by T also will remain the same definition, just to understand that this time interval that we are talking about is large now, and the corresponding distance travelled will also be in general large. We use a special notation for this. We change S to delta S. This S is written as delta S. Delta means a change. So, let us say a body has moved from one position to the other. So, the distance between the two positions, which will be the distance travelled by the body, will give you the total distance travelled, delta S, divided by the total time interval. You can now write as delta T. Understand that meaning wise, this term and this term both are the same. It is just a difference in the way we are representing it now. Why we are doing that, we will understand it when we talk about the second type of speed, the instantaneous speed. So, now in general, when we discuss average speed, we will be writing it like delta S by delta T, where delta T is a large time interval, in general it is large, and the corresponding distance travelled is delta S, which will also be a large distance. Okay. Talking about the units, as you can see, this value is still a distance by a time. So, its unit will still be meter per second. There will be no change in the units. It is a speed only. Coming to the instantaneous speed now. Instantaneous speed, as the name suggests, is the speed of a body at a given instant of time, at a particular time. So, this is the speed at an instant. Now, how do we find out the speed of a body at an instant? What we try to do is, in order to find the instantaneous speed, we take the definition of average speed itself, and we create a condition on this definition. We say that if this time interval delta T could be made smaller and smaller, and it is made so small so that it remains an instant of time, instead of an interval of time, a large interval, it remains an instant. Now, instant of time is a very, very short time, isn't it? A very small time interval can be called an instant of time. So, how do we make this delta T a small time interval? We put a condition on delta T. We say that if we can put a limit on this time interval, that it's approaching a zero value. What do we mean by this? I'll first write it down and then I'll explain it to you. So, V, which is now speed but instantaneous. So, if you just write INS as a subscript, this will denote instantaneous speed. Generally, when we simply write V, that also means we are talking about instantaneous speed. So, speed as such is instantaneous always. Average speed has to be called average speed as a term. Whenever we simply talk about speed, it is by default instantaneous speed that we are talking about. So, if we have to find out, what we do is we put a limit on the time interval delta T that it approaches 0. Now, what is the meaning of this expression, this term that I have written here? We are putting a limit on the time interval delta T so that it becomes so small that it becomes very, very close to 0. It is approaching 0. It's not becoming equal to 0. It's just approaching 0. That means it's very close to 0. Just next to 0 but not 0. In that case, we can say that this time interval delta T will become an instant of time. right? After we put this limit on delta t, we say that now we measure the quantity delta s by delta t. Delta s by delta t, because now once we have put this limit on delta t is a very small time interval, the corresponding displacement, not displacement, the distance travelled, delta s is the distance here, the corresponding distance travelled in a very short time interval will also be very small, and hence both the quantities are small, very small quantities, so small that they are approaching 0, but when we take their ratios, that will be a finite value still. So this limit being put on delta t, that delta t approaches 0, and then finding out the value of this expression gives us the instantaneous speed of a body. The speed of a body in a small, very small interval of time, and there is a special way in which we write it. When delta t becomes a very small a time interval, instead of delta t we write it as dt. And when the corresponding distance travelled also becomes a very small distance, instead of delta s we write it as ds. So then we get a new expression for instantaneous speed or just the speed. We get v as ds by dt. This expression reminds us of differentiation that we have studied in mathematics. ds by dt in fact is nothing but the differentiation of s with respect to t. Differentiation of s, the distance travelled, with respect to t. It is the same differentiation that we do in mathematics, differentiating functions with respect to the variable on which they depend. Okay. So, here we get a new expression for speed when we try to find out the speed of a body at a particular instant. See that this expression is still like a distance divided by a time. So, the unit of this expression will still be meter per second only, there will be no change in the unit, right. Okay. So, once we have understood this, the same definitions go for average velocity and instantaneous velocity as well. The way we have defined velocity, now we can talk about average and instantaneous values of velocity. So, average velocity, which we denote by letter V with a vector sign and with a subscript AV, V average will be the total displacement covered by a body over the time taken, the total time taken in covering that displacement. So, total displacement by total time, unit will still be meter per second itself, displacement by time itself, right. This time this is a vector quantity, this is what we have to understand. So, if we just have to write it in an expression form, average velocity will be the total displacement, which we will now write in form of delta s by delta t, the time interval, which is in general a large time interval. And since we are dividing a vector with a scalar, we are the average velocity will also be a vector quantity having the same direction as that of the displacement, right. Then comes instantaneous velocity. Instantaneous velocity on the same lines as we have studied speed. In order to study this, what we need to do is, we need to start off with putting a limit, LIM in short for limit that the time interval delta t approaches 0, it does not become 0, but it just becomes very close to 0, and then you find out the value of delta s by delta t, the displacement by the time, considering delta t to be very small. When you put this limit on delta t, the small time interval, very small time interval delta t becomes dt, and the corresponding small displacement will become ds. So, this is the expression that we will get for instantaneous velocity, ds by dt, which is once again nothing but the differentiation of the displacement with respect to time. Differentiation of the displacement with respect to the time t, right? Okay, so once we have got these basic definitions, now we can proceed further and understand a few more things related to this. Starting with the definition of speed, instantaneous speed, which is v is equal to ds by dt. Understand that the differentiation of a function with respect to any variable gives us, graphically gives us, the slope of that function within the graph. So, slope of the s versus t graph is given by ds by dt. This we know in general, that if we have y, which is a function of x, that means y depends upon x in any way, then the function dy by dx gives us the slope of yx graph, right? So, in the same way, here we are dealing with the distance time graph. So, the slope of the distance time graph, which is by definition ds by dt, will give us nothing but the speed. So, this is an important result that we get from here. What is the result? That the slope of distance time graph gives the instantaneous speed v, and the same result will follow for velocity as well. In case of velocity, we would be looking for the slope of the displacement time graph instead. So, slope of displacement time graph gives the velocity v, not the speed but the velocity. We can look at this from the graph as well. So, let us say we have a graph of distance versus time, which looks like this. This is distance line, this is the time axis, and let us say the graph is like this. We can take any shape of the graph. Just to take an example, if we want to find out the speed of this particle which is moving according to this graph at any time t naught, let us say, all we need to do is, if this is the point P on the graph corresponding to the time t naught, we need to draw a tangent at this point. A tangent would be a line that just touches this curve like this, and then we try to find out the slope of this tangent. How do we find out the slope? We extend the tangent so that it touches the timeline, find out the angle theta that the tangent makes with the time axis, and then the slope of this tangent is given by tan of the angle theta, right? So, if you are able to find out this function, this will give us nothing but the speed of the particle at this particular time instant t naught. Graphically, this is how we get it, right? The same is true for the displacement time graph also. In case of displacement time graph, the same slope of the tangent will give us the velocity of the body. So, this is one important result. Another important result is when we talk about the same relation, v is equal to ds by dt. From here, see that we can write this as ds is equal to v dt, right? Mathematically, this is how we get it. Understand what is the meaning of this. This expression means that a small displacement covered by a body is the product of its speed, instantaneous speed, with a very small interval of time dt, right? So, if we try to find out the total distance covered by the body, all we need to do is add the small distance covered ds and we get the total distance covered, right? Now, we all know this in mathematics, adding up all the very small distances travelled here mathematically would mean that we need to add all the small ds, which mathematically means we have to integrate ds. So, integral of ds would physically mean that we are adding up all the small distance travelled to get the total distance s. On the other side, this would mean integrating the function v dt. right? But mathematically, do we know that the integral of a function with respect to the variable on which it depends means we are trying to find out the area under the y-x graph? So, if we try to find out the integral of y dx, we would be getting the area under the y-x graph. On the same lines, here if we look at this expression, we understand that integral of v dt is nothing but the area under the vt graph, right? So, this means that, what does that give us as a result? This implies that area under the speed time graph gives the distance travelled by a body s, and the same result is applicable for velocity time graph also. In this case, it will give us the displacement covered by the body. Area under the velocity time graph gives displacement, right? So, these results that we have obtained here are very important results, because graphically sometimes it becomes quite simple for us to solve the question if we know these results already, right? So, one important result is that the slope of distance time graph gives the speed and the slope of displacement time graph gives us velocity, and the other set of results is area under the speed time graph gives us the distance travelled and area under the velocity time graph gives us displacement covered by a body.